This is just a short video on how to do the homework using StatCrunch in 9.2. Remember that we're using the t-distribution. Do you see the orange box in the upper right hand corner of the screen? This is very important. Whenever we're working with means and the population standard deviation sigma is unknown, we'll be using the t-distribution. So that's true in Chapter 9, Chapter 10, and Chapter 11. Anytime we're working with means and sigma is unknown, then we'll be using the t-distribution. Please read the slides and or watch the video for section 9.2 and read the handout about the t-distribution because it's all extremely important. If you want something that's very simple as an explanation, okay, all the t-distribution is a minorly modified normal distribution to take into account that we don't have sigma, and when we replace sigma by s as an estimate, when we replace the population standard deviation by the sample standard deviation s, then we need to modify the normal distribution to account for that fact, and that modified normal distribution is the t-distribution. All right, with that in mind, let's see how to use StatCrunch. You go to Stat, T-Stats, One Sample, Summary. How will you know to use summary? If you're given the sample mean, the sample standard deviation, and the sample size, then you use summary. If you're just given a list of numbers, then you use data. All right? If you're just given a list of numbers, you use data. But when anytime you're given the mean, sample standard deviation, sample size, that's summary. Then you put in the sample mean, sample standard deviation, sample size. Click on confidence interval. We'll deal with the hypothesis test in Chapter 10. Set the confidence level, hit compute, and you get your answers. This is more of the interpretations. Okay, this is more of the interpretations. Again, please try to pay attention to this in the homework. All right, maybe read homework help, etc. But this will not be emphasized on the tests and quizzes. So this problem just wants you to look at histograms and box plots. Now, if you've read this section carefully, you'll understand that when you're working with small samples, meaning less than 30, you have to assume that the parent population, all right, has a normal distribution, and you have to make sure there's no outliers in the sample. So here, they want you to look at a histogram. If you want to plot that, just go to Graph, Histogram. Look at this slide right here. Excuse me, look at this part of the screen right here in the lower left. And if you want to do a box plot, just click on box plot and follow the instructions on this diagram right here. So when you're given just a list of numbers, you'll export that list of numbers to the first column in StatCrunch. Then you'll still go to T-Stats One Sample, but now you use data. You indicate what column your values are in, set up the confidence level, and hit compute. It'll work the same as before. The only difference is you don't do summary because you have a list of numbers. So this is about determining sample size. Even though we're working with the t-distribution, because the t-distribution numbers change with respect to sample size, they're not stable, you have to actually switch back to the z sub alpha over 2. It's a little bit strange, but don't be alarmed by this. All you've done is taken the margin of error formula and solved it for little n sample size. They will give you little s, they will give you e, and they'll give you the confidence level. You put those numbers in, square it, and that's your sample size. But always round up. It has to be has to be the smallest integer that's greater or equal to the number you get from the calculations. So even if it says 99.01, you have to go up to 100 because you need an integer value greater than or equal to the value that you solve for when you use this formula. A few additional hints on how to do the homework. This is problem 4 in section 9.2. If you remember in section 7.3, which was titled Assessing Normality, we talked about answering the question, is it reasonable to assume that the parent population has a normal distribution when we're working with a small sample? And we used a normal probability plot. So that's what we're doing here. We have a small sample, 25 observations, and based on the normal probability plot and the box plot that we're looking at right here, we want to know, is it reasonable to assume that the parent population has a normal distribution? Well, the reason we're looking at a box plot is because we're not allowed to have outliers. Right, so we don't have any. They show up as little stars or asterisks on either the left or the right end. But look at the normal probability plot that we have in the center of the screen. We want to know, is that sufficiently linear? And if you remember from section 7.3, we compared the correlation coefficient, here it's 0.993, with something called a critical value. So you open up the table of critical values and you match it to the sample size, 25. And so here the critical value is 0.959. Yes, the correlation coefficient of 0.993 exceeds the critical value, and therefore this normal probability plot is sufficiently linear for us to assume that the parent population is normally distributed. What we're looking at here is problem number 16, and this is a little bit strange, all right? And that's why I'm trying to help you out here. So I want you to look down here in part C. Do you see where it says 23.360 minus, and then down below 23.360 minus and plus here, and then 2.576, 2.576, and then on top here 4.908, and then 26.990, and then out here equaling 23.283. They're constructing the confidence intervals by hand. All right, and so the 23.360 that you see in the top and the bottom here in part C, that is the X bar, which you see up in the top. See, right there, X bar 23.360. Now, this margin of error that you're seeing as 0.077, they're computing it down here, right, by hand. And so you have something called T alpha over 2. See the 2.576. We'll address where that came from in a minute. But you have X bar plus or minus T alpha over 2 times S. This is S right here, 4.908. Right? See up at the top, standard deviation, 4.908 over the square root of the sample size. They did the math on that, and that's where the 23.283 came from. Now, if you remember from section 9.1, when we had a confidence interval and we wanted to be 90% certain, the Z alpha over 2 equaling 1.645. Okay. When we had a 95% confidence level, we had a Z alpha over 2 equal 1.960. And when we had a 99% confidence level, we had a Z alpha over 2, 2.575. Sometimes that's listed as 2.576, but let's not be too concerned with that. What I want to talk about is the equivalence between T alpha over 2 and Z alpha over 2. This is a very large sample size. Look at the sample size here. It's 26,990. Okay. What you have to understand is for large samples, anything over 1,000, say, T alpha over 2 equals Z alpha over 2. They're just the same once you get an extremely large sample size, and that's what we have here. So they're just using the numbers from section 9.1. When this problem's randomized, meaning every single person does it, it will have different numbers. Sometimes they want 95%, sometimes they want 90%, sometimes they want 99%. Just use those three numbers from section 9.1, the 1.645, 1.96, or the 2.575. There's a tolerance setting here, plus or minus 1 in the thousandths place. That's the third place over. So I'm telling you it's 2.575. They're using 2.576 here. Don't be alarmed. They'll both give the right answer.